Here is a simple problem in which a mass is supported by a wire and a cord. When the cord is cut, this system becomes a pendulum. We want to determine the tension in the cable before and after the cord is cut. In order to solve this problem, we first need a good free body diagram. Here are the steps to get it perfect every time. First, isolate the body or area of interest. Second, draw an outline of the isolated portion of the system. Next, show and label all the forces, both known and unknown. Then, show all critical dimensions necessary for solving the problem. And finally, attach an appropriate coordinate system. This can be rectangular, normal, tangential, or some other coordinate system if it makes solving the problem easier. We will demonstrate this with this example. Before cutting this cord, the mass is in equilibrium, so this is a statics problem. The free body diagram of the mass is shown here. All the three forces acting on the body are shown. The only dimension that we need is the angle theta, which is also shown. What we need in this diagram is a coordinate system. The obvious choice is a rectangular coordinate system in this case. Let us go ahead and use it. Take a look at the final free body diagram for this problem. We can now solve for the tension in the cable by summing up all the forces along the y-axis. Now, let us draw the free body diagram after the cord is cut. Notice there won't be any force acting along the cord as it has been cut. The free body diagram for this scenario is also shown. We now need a coordinate system. In this case, a normal tangential coordinate system will make the problem easier to solve. So we will use it instead of a rectangular coordinate system. The final free body diagram is also shown here. After drawing the free body diagram in kinetics, we want to show the acceleration so we can proceed to write the equation of motion. Notice, I have shown both normal and tangential acceleration vectors on the free body diagram itself. This is essential so you can use it to develop the right side of the equation of motion. We can now solve for the tension by summing up the forces along normal direction. Notice on the right hand side, we have the normal component of the acceleration. However, at this instant when the cord is cut, velocity is equal to 0. This equation can now be used to solve for the tension by directly applying Newton's second law.